Today we're going to have a quick look at the Kuhn-Tucker sufficiency conditions. Now in the first video I made, we considered solving the necessary conditions for some NLP. Now, even though you have solved these necessary conditions, it is not guaranteed that the solution you obtain will be the correct solution. However, the solution will have to satisfy those conditions. If, in addition, it satisfies the sufficiency conditions, you know that the solution is correct and is the solution to your NLP. So let's look at a generic minimization problem. Minimize f of x, where x is some vector in Rn, x1 to x3 for instance, subject to some constraints. Gi are functions of the vectors x, and they are all smaller than or equal to bi. Now once we have solved the Kuhn-Tucker necessary conditions for this problem, how do we determine that those are sufficient to solve the problem? Well, first of all, we're going to need that f is convex. Now this is exactly like in the normal case, in the linear case where you had R1, if you had to minimize a function, you knew it had to be convex, because only then would it have a proper bottom to the function there. Now in this case we need f convex, but we also need another condition. We need that the gi are convex. Now this is a slightly technical requirement, but that will usually be satisfied in the problems you'll consider. For instance, we know that all linear functions are convex, and very often the constraints we encounter are linear. For instance, quadratic functions are also convex as long as the leading coefficient is positive. So all this really says is that your function has to be almost a bowl shape rather than a cup, an upside down shape if you want to do a minimization, and that the area over which you want to do the minimization, which is the constraints, also has to be convex. This is because the Kuhn-Tucker conditions are part of convex optimizations and don't necessarily work if we don't work in a convex region. Now, in exactly the same way, if you have a maximization problem with the same conditions, the same types of conditions, now you will need to have that f is concave. In other words, that f is something which looks like this but in more dimensions. So you will be able to get a proper maximum there. Now you might expect that in this case you would have that the gi would be concave, but this is still a convex optimization technique, and so it is still necessary that the functions gi all be convex. Now, how does this relate to what we've been doing with our problem so far with the Hessian? Well, the Hessian is used to determine when the function f is convex and when it is concave. So let's just go through that quickly. A function will be convex if and only if it has continuous second order partial derivatives in all its variables, and the principal minors are all non-negative. Now note I don't say positive, I just say non-negative, so they have to be greater than or equal to 0, not necessarily greater than 0. Now I'm leaving up a technical point here. What the real technical definition would say here is that f is convex on a region S in its domain of definition if the continuous second order partial derivatives exist at all x elements of S and the principal minors are all non-negative at each x element of S. Now in our case we work with fairly nice functions, so this is usually not an issue. However, you should take a look at this if you're dealing with functions which have slightly different domains of definition, which might contain some points where the function is not nicely differentiable. Now f will be concave if and only if, again, we have the partial derivatives condition, second order partial derivatives must exist and be continuous, and all non-negative principal minors have the same sign as -1 to the k. I should put there kth principal minors. Okay. Now, what does this mean in practice? First of all, just note that here again it says non-negative, so only the principal minors that are strictly greater than 0 will be considered. This is because, for instance, you have, if you look in 2 dimensions, if you apply this rule to a plane, you'll find that it actually satisfies both of these conditions, and that is because a plane can be considered to be both convex and concave. When you're looking at just a flat piece in R3 as we have here, it'll actually be both convex and concave. Now, if we before I go further, let me just give an example or an illustration of what a principal minor is. So we have been working often with 2 by 2 matrices, and in this case the principal minors are easy to calculate. It's just x11, x22 and x11, x22 minus x21, x12. Now you'll notice that the second one is just the determinant. So to get the principal minors for the 2 by 2 matrix case, we just take the diagonal elements, those are the first principal minors, and the second principal minors are the determinant, which is just this crossover product. Now in the case of a 3 by 3 matrix, how will you determine the principal minors? Let's just write down the matrix here. It gets quite a lot more complex in terms of determinants the moment you go up a dimension. So in this case, the first principal minors will still be the diagonal elements. The second principal minors you will obtain by determining the determinants of the matrix with some rows and columns removed. So in the first case, we remove the first row and the first column, and we're left with the matrix x2, 2, x2, 3, x3, 2, x3, 3, and we take that determinant. So that just becomes x2, 2, x3, 3 minus x3, 2, x2, 3. And we have to do the same with all the other columns and rows. We have to remove the second column and the second row, and then we'll get determinants of x11, x13, x31, x33, which you can write out, and also what happens when we remove the third column and the third row. I just get the submatrix x11, x12, x21, x22, and take that determinant. So these are the second principal minors, and the third principal minor will just be if that's the matrix A up there, the third principal minor will just be the determinant of the matrix A. So for the function to be convex, if these represent the partial derivatives, the diagonal elements will all have to be larger than or equal to 0. These three determinants here will have to be larger or equal than 0, and the determinant of the whole thing will have to be larger than or equal to 0. For a concave function, we know that these ones will have to be negative, the second ones will have to be positive, and the third one would have to be negative again. Now let's just look at this in the context of one of our problems we had earlier. So if we look again at the problem we had in the very first video, we had a minimization problem, x1 minus 3 over 2 squared plus x2 minus 1/2 to the 4. Now this is a quadratic function plus a fourth order function, and if you've worked with these functions a bit, you can actually immediately see that this will be a convex function, but you have to verify this by looking at the Hessian. Now in terms of the sufficiency conditions, we can see that our constraints are all linear, so they are convex functions. So all that remains for us to determine that our solution that we found using the necessary conditions is correct is to determine that this function is in fact convex. Now this is quite easily done in this case. Fortunately, we have the derivative of z to x1 is 2. The derivative of z to x1, x2. Now here's a bit of a shortcut. In case your functions have continuously differentiable derivatives, like in this case, like with polynomials, the second derivative, d squared z dx1 dx2, will always be equal to d squared z dx2 and dx1. So you actually only need to compute one of them. In this case, they're both just 0. And then d squared z dx2 squared is equal to 12 x2 minus 1/2 squared. And now we can form the Hessian. So this is, first we get the matrix. Often some people refer to the Hessian as the Hessian matrix. Some people refer to the Hessian as the determinant of the matrix. It doesn't matter too much which one you use, which terminology you use, as long as you're clear in your steps. Now, what are our first principal minors? Well, they're just 2 and 12 times x2 minus 1/2 squared. Obviously, the first one is larger than or equal to 0, and the second one is just 12 times some number squared, no matter what x2 is, and that will always be greater than or equal to 0. The second principle minor is the determinant of this whole matrix, and that's just 24x2 minus 1/2 squared, and by the same reasoning this will always be positive no matter what value for x we can plug in there. So therefore the function z is convex, and since our constraints gi are all convex as well, the KKT sufficiency conditions are satisfied. Now what does this mean? That implies that the solution in video 1 does indeed solve our nonlinear program.